Welcome to the presentation of our paper Ontology Matrix as a Service, where we present a newly developed REST interface for the calculation of in total 81 distinctive ontology matrices. This research is a product of a collaboration between the Rostock University and the Robert Bosch Corporation. The presentation is structured as followed. At first, I'm going to explain the historical background of the tool and the trigger for the developing of the extension. Secondly, I will motivate the rising need for ontology matrix through the rise of semantic technologies. Introducing the theoretical background of the tool, I will then talk about the implemented different kind of ontology matrix, as well as give a few examples. This is followed by a practical guide, how to access and use the newly developed tool, and an outlook on the next planned research steps. The initial OntoMetrics platform was first published by Birger Lanto in 2016. It is written in Java and utilizes the OL API for the handling of the ontology-related calculations. If you want to analyze an ontology, you can either paste the ontology content into a text box, upload an ontology file, or provide a link to an online resource. For quite some time, the tool was available but not developed further. Then, in last summer, the Research and Development Department of Robert Bosch Corporation contacted us regarding a request for collaboration on the topic of ontology evaluation. They use ontologies for various purposes in almost all business units, and there were a need for an evaluation tool. And OntoMetrics was one of the very few evaluation tools that were still available and usable. So, how do we get here? Why are semantic technologies increasingly used? And how does it motivate the new need for ontology evaluation? In the past years, a lot of emphasis was on sub-symbolic approaches, like machine learning. However, these approaches consume vast amount of training data and are not context-aware. Further, the decision processes are not transparent. While trends like explainable AI are working on resolving the black box problem, semantic technologies are human understandable in its core. The flexibility of semantic technologies led to various application scenarios, like smart factories, where semantically annotated sensor data offers a more abstract view on a production process through the integration of SAP master data and the mapping of components to machinery, sensors, and products. Another example is autonomous driving, where we can model the proper behavior for an autonomous car. The rise in ontologies, though, does not come without problems. In a classical ontology development process, a knowledge engineer works together with a domain expert to create an ontology artifact. This process is time-consuming and costly. Additionally, knowledge engineers are a scarce resource. Increasingly, these artifacts are therefore developed by domain experts alone. Developing methodologies like Diligent already reacted to this change of behavior and retreat the knowledge engineer to an advisory role. We therefore argue that ontology evaluation is now more important than ever to control and measure these grassroots modeling efforts, and especially to support these new ontology developers. As mentioned before, OntoMetrics is one of the few tools available that still offers support for the numeric analysis of ontologies. In the table on the right, you will see that even though the area of ontology evaluation has seen a lot of research effort, these tools are often heavily outdated or no longer available. Further, there are a few tools that allow the calculation of matrix as a side product. A good example is the tool Protégé, which calculates axiom-based matrix like count of subproperties or the count of object property ranges. We believe that calculations like these can further help to understand modeling efforts. If we see that the logical axioms count is low in comparison to the count of classes and axioms in general, one can, for example, infer that this ontology is used more as a taxonomy rather than for logic programming. A trained knowledge engineer can quickly generate improvement ideas. We therefore believe that metrics like these should be part of more applications. However, developing a metric calculation engine is time intensive. We therefore want to lower the entrance barrier for the consuming of ontology matrix and enable programmers to quickly implement such features in the form of a service. This formed the idea to extend the OntoMetrics graphical user interface with an additional REST interface. On this slide, you see the different categories of matrix that OntoMetrics is able to calculate. Base metrics comprise of the count of certain ontology aspects, for example classes, individuals, data properties, or more specific items like data property range axioms. They already give a very clear indication of the modeling style and expressivity used in the ontology. However, the base metrics have a strong need for interpretation. It is, as an example, likely that a large ontology with a lot of classes might also show more logical axioms than a smaller one, even though the smaller might be more expressive. Schema metrics take this into account and performs a calculation based on percentage values rather than absolute ones. An easy example for this kind of matrix is the class axiom ratio. Graph metrics focus on the attributes on the hierarchy tree. Is the tree more width or depth? What is the total and average number of paths? The knowledge-based metrics are concerned with the analysis of the individuals of the ontology. It can answer whether the individual just populates specific parts of the ontology or the whole, or the ratio of classes and instances. At last, the class metrics focus on specific elements on the hierarchy tree and are calculated per class. For example, how connected is the specific class towards others? How much of the overall individuals are related to the specific class? The calculated metrics are mainly based on the works of Gangemi and others, and Tartier and others. If you're further interested, I'd like to recommend to you the original works of these authors or the OntoMetrics wiki, where you find a detailed view on the specific calculations. Okay, how do we access the newly developed REST interface? There are two possible ways to access the metric calculations. First, it is possible to provide a link to a given ontology. Doing so, you can use a simple GET request shown in the slide. However, a lot of ontologies might not be publicly available but saved locally. These ontologies can still be examined using a POST request with the ontology content in the body. By default, the class metrics are disabled. Their calculation requires more computational power and therefore increases the response time. Transmitting a header value with class metric equals true, the calculation of these metrics can be activated. By default, the calculated metrics and ontologies are internally stored for scientific purposes. This behavior can be disabled by adding a key save with the value false. The response contains a header with the key value pair saved, indicating whether the ontology was stored on our servers or not. Let's have a look at a real-world example. Here you see the Firefox extension Raster, and we're going to access the friend of a friend ontology. The next research steps are the analysis of the data that has been collected so far. Further, we are currently extending the tool to access JIT-based ontology storages for a view on the historical evolvement of metrics. We believe that the holistic view on the ontology development process allows to infer a data-driven quality model. This closes the presentation of the newly developed REST interface for ontology metrics. We hope that you find it interesting and maybe even see an integration possibility for yourself.